Alright, so I guess I'm the last person between you guys and lunch. I have to warn you, I have quite a few slides that I wanted to show you, so I guess you decide if you want something in your brain or something in your belly. So we'll see. Alright, so let's get started. I'm going to talk about the implementation framework, specifically about OpenFresco and OpenFresco Express, the graphical user interface. The outline of the presentation is as follows. We will first go a little bit over the OpenFresco software framework, look at the architecture and what it does and how it works. Then I have a few slides on some very unique OpenFresco features. I probably can go quickly over those because Sean already touched on some of them. Then I'll show you a few slides on the OpenFresco Express graphical user interface that we developed, which is very helpful for classroom things or when you do simple hybrid simulations in the lab. Then I have something on the website, OpenFresco website, and other locations where you can find other resources that might be helpful when you do hybrid simulations and give you the summary and conclusion in the end. So let's start with the OpenFresco software framework. So what is OpenFresco? OpenFresco stands for the open source framework for experimental settlement control. And the development was started many years back together with Steve when we felt like there was a need to have such a framework because every implementation that had been done previously was very specific to a laboratory, to a specific hybrid test that people were trying to do. So a lot of people, when they did hybrid simulation, every test they started over again from scratch. And so we felt this need that this framework should be developed, a middleware that allows you to connect your finite element software to the laboratory in a more streamlined way. And so that's how originated OpenFresco. So it's a secure object-oriented, network-enabled middleware that can then really pair the software where you do your finite element analysis with the control system and the data acquisition systems in the laboratory. And you can see currently we have a lot of computational drivers that can be paired with OpenFresco. So you can do your finite element analysis, your numerical simulations, in OpenC's, OpenFresco Express, which I will go into. You can do Abacus, ANSYS, we've heard from Sean, LS-DYNA, you can do MATLAB, Simulink, UI SimCore, so we have a lot of choices there. The same thing is true on the other side of the test, right? In the laboratory itself, where the control system and the data acquisition systems are sitting, we have a lot of interfaces there too that OpenFresco can talk to. So we can talk to DSpace digital signal processors, we can talk to the whole family of MTS systems there, so we can talk to an SDS family systems, we can talk to FlexTest, we've seen that through CSI, we can talk to FlexTest through ScramNet, we can talk to a hybrid, to the shake table controller, the 469D, which we will actually talk a lot more about tomorrow, and we will see a demo, how we talk to that. Or we can talk to specialized MTS controller, for example, at the SR&D at UC San Diego. We can also talk to National Instruments controller, Pacific Instruments controllers and data acquisition systems, and then some specialized ones that we've developed that are more generally used in Europe, for example, this AD Win there. So as I said, why do we need a framework? Like I've already touched on this, there was a lack of a common framework for development and deployment. And so that's how we started developing OpenFresco. And so with that, we created this very robust, transparent, adaptable, and easily extensible software framework that we use for research and deployment. A software framework, what is that? It's a reusable system, a software system, and it defines the overall architecture of the software. So it defines this in terms of components and relationships that are between those components. And that's typically expressed as a set of abstract classes and the way those abstract classes interact with each other. And typically we want a very loose coupling between those components when we develop a software framework, which makes it then very easy to extend this framework and adapt it to other problems, and also reuse it. So when we started doing all this, we really started rethinking how we want to implement this strategy. A lot of people, when they were doing previous tests, they more often approached the hybrid simulation more from the control system side. for us, when we started doing this, we thought, well, let's approach this more from the finite element software engineering side. And so typically, when people do finite element analysis, purely numerical simulations, they use some finite element code. And in your finite element code, you typically have different things that you need to define. So you have your nodal geometry of boundary conditions, you define mass and damping properties, and then you put in some loading conditions. And eventually you will get down to where your element and material properties are in your finite element software. And so you will define different parts of your structure with different elements and material properties. So you have maybe one area in your structure that you can describe well with one numerical element, and another area with another numerical element. But then eventually maybe there is some place where you're not quite sure how to do this numerically in your finite element software. You don't have the right element, you don't have the right material yet. And so that's where it comes in that you want to maybe test this to really find out how does it behave. So you define this part as an experimental element instead of a numerical element. And then you go into your lab, and that's where you put your specimen. You build that part of the structure, and you have your controllers and data acquisition systems. And now the question comes, how do I connect those two? And that's really where OpenFresco comes in. So it's really a middleware that it cannot do by itself a hybrid simulation. It relies on other parts. It needs a finite element software that it connects with, and it needs the laboratory with the data acquisition system and the control systems. And so that's how we then send out commands from our finite element software through OpenFresco out to the laboratory, and feedback such as forces typically back from our laboratory into our finite element software. If we now look a little bit more into what are the components inside the software framework. So at the very top, again, we have the finite element software that has all the features of a typical finite element software. At the very bottom, we have the control and data acquisition systems in the laboratory, as we know them. And so what's in the middle inside OpenFresco? We decided to break this up into different components. So we created a bunch of abstractions of the actual real physical world. So for the first abstraction that we created is the experimental element. Instead of a numerical element, you have an experimental element, which now basically represents your specimen in the laboratory, basically what you're testing. Then we said, well, you're going to do this test somewhere. So you're going to do it in a laboratory. So that's basically the abstraction, the experimental site. Where are you? Are you in a local laboratory? Or if you do a geographically distributed test, are you at a remote laboratory? So that's the experimental site. It also stores data as this process goes on. So it's kind of a place where stuff gets stored as well. Then in the laboratory, typically then you have some experimental setup, because usually you then have to, your degrees of freedom that you're trying to control are different than your actuator degrees of freedom. So you've got to do some conversions. So you basically build up an experimental setup in the laboratory. So in the software framework, again, there's an exact abstraction of this real thing, which is called the experimental setup. And is responsible for transforming degrees of freedom from typical element degrees of freedom to actuator degrees of freedom. And Sean already talked about this quite a bit. These transformations can either be done in a linear or non-linear fashion. And then finally, we have the abstraction of the experimental control. And that's really there to directly interface with whatever controller you have in your laboratory. So what are some requirements for the architecture? Well, it should provide connectivity to very wide array of different finite element software, and we are basically achieving that, as I already showed. But it also should also enable us to do distributed testing, so that's another requirement, and it should interface with the rapidly evolving control and data acquisition systems that are being developed in the laboratories. And so for that, we basically came up with this multi-tier or three-tier software architecture that we wrapped around core elements in OpenFresco. And with that, we can do a lot of different deployments. So we can do different local deployments. As you can see on the very left, you have a finite element software like Sean showed, where you put in some generic client element and you use OpenFresco to talk to the laboratory. If you want, you can directly implement an experimental element into your software instead of a generic element, so we allow that as well. Or if you use OpenCs, because both OpenCs and OpenFresco are both object-oriented programmed in C++, we can actually more closely tie these together and achieve faster performance when we do that. So we have all these different options. Then for the network deployment, so if we want to do a distributed test, we can do the same thing. So left column is using the generic client element, middle one is using the experimental element, and that's OpenC's on the very right. And so here now we split it up. So at the site, instead of using a local site, before here on the local deployment we were using a local experimental site, so that gets now split up into a shadow experimental site and an actor experimental site. So the actor sits basically where your actuator is in the laboratory, and this is a shadow where your final element software is. So we can split it up, and we can use different sockets and channels to do this communication there over the network. I can skip over this. This is just showing you the OpenFresco class diagram, all the different stuff I just showed you. I just wanted to have it in the presentation for people to look at later. So now if we go into a little bit more at what every component is actually doing inside OpenFresco, starting with the experimental element component. So the experimental element, first of all, it has to transform. This doesn't really change much from a regular numerical finite element. Basically, it has to transform from your global degrees of freedom in your finite element software, typically to some basic degrees of freedom. And so if we look at, for example, let's do a 2D example here, and we look at this inclined member here, this basically a beam column element. And so we start off in our finite element software, typically we use a 2D problem in this global coordinate system. Like 6 displacement degrees of freedom and then 6 force degrees of freedom. So now we basically have to transform this because it's a frame element. We do some transformation and we remove the rigid body modes. And basically we can do this in two ways. One way is we go in removing the rigid body modes going to the simply supported system, or the other way that we are choosing here in the experimental element, we go to the cantilever basic system. The reason being, if we remove the rigid body modes going into the cantilever basic system, we actually end up with 2 displacement degrees of freedom and only 1 rotation degree of freedom. And it's easier to control a displacement degree of freedom than a rotation degree of freedom. So this is the preferred basic system. So that's what we do. We transform into that. That's what the element basically does. Once we're there, we have then the experimental site. As I said, it stores data and provides these communication methods. So if it's a local site, it's sort of a dummy. It doesn't really do much. But if it's a geographically distributed hybrid simulation, that's where we break it up and we use different protocols to communicate across a channel. So we can use TCP/IP, we can do TCP with SSL, secure socket layers on top, or we can do UDP if we need to achieve faster performance and are not so worried about package loss. With that, then we can test all over the world, as we've seen before. The experimental setup is then the next thing. So now we need to transform from our element degrees of freedom, which we looked at up here, to our actuator degrees of freedom. So going back to our element, which again is this inclined member, and starting off again with the basic system. So we have these 3 degrees of freedom now. And so now we got to somehow put this element into the laboratory. So in the laboratory, obviously we will turn this around, make it vertical, and we now want to control 3 degrees of freedom at the top here. So there's different ways of doing this. One way is we put a big cross beam on top, loading beam there, and connect 3 actuators as such. And so now we have to transform from the degrees of freedom at the element to these actuator degrees of freedom. If this is a linear transformation, Sean showed this already, it's actually just a transformation matrix and it's very easy to do. And we have to do the same thing when we come back and we measure forces, and basically on the 3 actuators, those forces need to be transformed back into 2 forces and a moment at our element level. And again, that's just a transformation matrix. If we want to do this in a nonlinear fashion, it becomes more complicated, and we can do that. So that's the experimental setup. Then finally, the experimental control, like I said before, it basically then interfaces with your actual controller in the laboratory. And one way of doing this is basically talking, for example, to an XPC target, which is a digital signal processor. We'll see this more in the demo this afternoon. We can directly then talk through this experimental control object to the controller in the laboratory. So that's there. Then I want to say a few words about computational drivers. I've already touched on it, and Sean has touched on it. We have a lot of computational drivers that we allow to interface with. And so there's two ways to do that. We can do this either through an implementation of a generic client element into any finite element software. So if you have a commercial finite element software, that's your favorite finite element software that you want to use, as long as it has an interface to do a user-defined element in that software, you can then implement this generic, or what we call a generic client element, into your commercial finite element software. The other way is that you could do an experimental element directly. We have this for many software packages that are available, already done. So these implementations are available if you download the OpenFresco source code and you go into this location under SIM application clients. We have all these implementations there available. What do we have available? Well, obviously OpenCs, because that's very easy to do. We can directly talk to OpenCs using function calls. We have an implementation with LS-DYNA, so that's available. We have implemented a connection with Abacus, so a generic client element is available in Abacus, and we can do that. We can do MATLAB and Simulink, so if you have your own implementation of your structure in MATLAB or even in Simulink, we actually have block, for example, for Simulink, we have blocks that you can drop into your Simulink model that then do a TCP/IP connection to OpenFresco and talk to OpenFresco like that. We also, Sean touched on this, in collaboration with MTS, we finally implemented the connection with ANSYS, so that's available as well. Salim already talked about this quite a bit, so I'm going to go quickly on this. A few words about integration methods. He touched on it. Oftentimes when we have structures where we don't have mass on rotational degrees of freedom, it can happen that our mass matrix becomes singular. And so our differential equation that we're trying to solve is basically becoming infinitely stiff, and that then requires that we use fully implicit numerical methods. Another important thing when we look into integration methods is that we do make as few function calls as possible. By function call, I mean basically we're sending out displacements and we want to get back resisting forces. The fewer we can make that means the fewer communications we have to the laboratory. And that means we can go quicker and we can have less problems. Another thing is that the use of constant Jacobian is also not always possible, so sometimes tangent stiffness, like it was mentioned before, is not available, and we basically then rely on a constant Jacobian instead of adjusting that. We have implemented many of these integration methods into OpenCs, so they're available there. That's one advantage of using OpenCs over some other more general purpose finite element software packages, that we do have all these specialized methods in OpenCs available for hybrid simulation. So we have a whole range of explicit integrators. The more recent one that we just added is this KR alpha method that was developed by a student of Jim Rickles at Lehigh University. So very new method that's available in OpenCs. We have several implicit integrators that are the general ones, which you should not be using for hybrid simulation, such as a Newmark method, alpha methods, and so on. But then we also have the specialized ones, which we adapted to make them work with hybrid simulation. So there's a Newmark method, which is called HS, and so on, that are then available for hybrid simulation. And then we have some operator splitting methods there as well. So all that is available in OpenCs. So a few words about the unique, more unique features of OpenFresco. Very quickly, we can actually do, when we have similitude and scaling issues or that we need to consider, because we're doing our experiment at a smaller scale than full scale, so we need to consider similitude loss, which is very important. We have ways in OpenFresco inside basically the experimental setup to put in factors to account for descaling or similitude loss that we need to consider. And so we can do this typically either on one before we do the transformation. So again, this is the experimental setup, right? That would be transforming from your element degrees of freedom to your actuator degrees of freedom. And so you can either put factors on these quantities here before you transform from the element degrees of freedom, or you can put factors on the quantities after your transformation, meaning your actuator degrees of freedom. And depending on what you do, basically for similitude loss, it's better to do it. It typically works better to do the factors over here. And if you do other scaling things, then it's better to do the factors over here. So both of those are available in OpenFresco. I sort of can almost skip over this. Sean showed this in very detail. Another really nice feature of OpenFresco is that you can actually perform co-simulations or software coupling, where you, instead of having an experimental specimen in your laboratory, you're simulating your laboratory experiment using another finite element software. So that's also available. And this same thing as like all these connections that we have on the client side, we have basically adapter elements implemented to do these types of co-simulations for the same types of software. So we can do adapter elements, we can simulate a specimen in OpenSys, Abacus, LS-Dyna, MATLAB, Simulink, and ANSYS. So we have that available. The test rehearsal we have already heard a little bit too. Another very nice thing to do with OpenFresco is to use this to do an actual dry run before you go into the lab and do your real test. And when you do a dry run, oftentimes it's very important that you simulate your dynamics of your controller, your dynamics of your actuators, maybe even the hydraulic power supply, everything is in there. And so MDS has actually developed very nice Simulink models to really capture all these dynamic effects coming from the control, from the actuators, and so on. And so these Simulink models sit here. And what we basically did, we can now connect from your finite element software using OpenFresco. We can connect to this Simulink model that then simulates the actuators and everything. And then at the back end, we create another connection here to another finite element software which then simulates your specimen, like this. So now you really have a full dry simulation with everything in there, and it can be very, very helpful to assess everything before you go into the lab and do your actual test. Another thing which is special, which we have in OpenFresco, and we're just slowly starting to bring it into OpenFresco, is force control and mixed force control capabilities. So Hong Kim, a former student here, he basically developed this, and it has been around for a while now, but we haven't had time to basically roll it back into the OpenFresco code. It's been sort of sitting on a branch development, but I'm now currently bringing this back in, and so we have these capabilities starting to have those available as well. So if we want to do, for example, it's a very nice thing we've been talking about, it's very hard to do a tangent stiffness matrix in a hybrid simulation. So now we have some capabilities basically here. Your experimental element, you can see, we have actually an experimental tangent stiffness class. And this experimental tangent stiffness class has different methods, like subclasses here, EFGS, Freud, and transformation solve, and so on, that can calculate the tangent stiffness on the fly. And so by connecting this new class with our experimental element, we now, in the experimental element, have the choice. Do we use the initial stiffness matrix, as we've been doing it for many years, or do we want to try to calculate a tangent stiffness on the fly and make use of that? Some other more recent additions to OpenFresco are maybe some utility commands that we've put in. So we can actually create log files which log everything that is going on in OpenFresco. There's a way now to define default units. So you can put in your default force, length, time, and temperature units. And that allows you to access all the units basically by just typing. When you create your commands for different things, you can do your unit calculation directly. You can also add metadata if you want. You can give your test like a title, a contact, description, and so on. We have a new command to record. When you want to do a single recording instance at any time, you can basically execute a record experimental command, which then records all the experimental stuff. You can remove these recorders if you need to destroy them later. We have a new command to wipe your experimental element stuff, so everything like the site, the element, the setup, the control will be removed. So that's to clean up things. And then we have some new commands that we implemented to start it's not quite there yet, but to start doing sort of a step during a hybrid simulation where you want to step your hybrid simulation, or you want to pause your hybrid simulation during a test and go in and see what's going on and then continue it. So we started implementing commands to achieve that. Okay, then next thing, hybrid simulation using OpenFresco Express. So we also have this graphical user interface that we put together called OpenFresco Express. It's programmed in MATLAB, it's graphical, and we will be using that for the demos actually, or not for all the demos, but for one of the demos. We will see this afternoon when we're going to be using this. So this is a really nice thing, especially for doing very simple tests or for educational purposes. So we have this available. Currently it has 3 simple structures. One is just a 1 degree of freedom type of column. So you basically come into your graphical user interface, you define, select what structure you want to define. You can scroll through the different types of the 3 structures that you have by the scroller here. Then you assign your mass, your stiffness, and it will calculate your damping, your period immediately from that. And then you assign basically your damping values there. So that's that. For the loading, you can do 2. So you go then basically you march down along these buttons here. You start with the structure, you go to the loading. For the loading, you define, well, do you have ground motion or do I want to do a free vibration? And that's what we will be doing in the demo this afternoon. So a free vibration, you specify what the shape of your free vibration should be. You specify a ramp time that you ramp up to this displacement, and then you specify how long you want to do your free vibration. And we will talk about this a lot more, Salim and I, when we have the demo and why we want to actually do that. So that's that part. And then you go to your experimental setup. That's nothing really for you to specify for this simple structure. It's just one actuator. So it's just giving you a picture. And then you go to the control. And for the control, you have 2 choices. You either do a simulation or you do a real controller. And so, for example, you want to do a real control, talking to a real controller in the laboratory. Maybe you choose your MTS CSI to talk to CSI that Sean you showed. And so you select that, and then the mass comes up, and you basically have to then define the different parameters for whatever controller you chose. So for the CSI, you basically give it your CSI configuration file, you tell it where that file is located, and you provide a ramp time for the CSI. And so that's the input it needs there. It's all nicely graphically available, and you can load that in. Now you're ready to run an analysis. So you come to the analysis page. It basically tells you what the DT is that is being used. For this simple graphical interface, what we're doing internally, thank you, will be that we are always using that explicit Newmark method that Salim has mentioned and Sean has mentioned as well. So that's what's implemented in there. And as you remember from Salim's talk, the explicit Newmark method is actually conditionally stable, so we need to satisfy that, and so it immediately calculates that for you from your modes that you have for your structure on the first page, and it tells you, okay, my integration time step size needs to be smaller than that limit there. Once you have that, you basically write your Tickle input scripts. So you click on that. If you want, you can also optionally create, you can optionally look at a report of what all the different parameters are that you define. And then when you're ready, you basically click your play button, and that will start your test. As soon as the test starts, there will be 2 more windows that pop up. One is for your structural output, where you can see in real time as you run this what your output is in terms of displacement, force, acceleration, and it shows you also along the way where you are on your ground motion. And it will give you the hysteretic behavior. So it will basically plot displacement versus force on that plot. Then there will be a second plot where it shows you error monitors. And I had to sort of overlay this because I ran this in simulation, so there was no errors. So for you to be able to see this, I overlaid this with some actual tests. So for that, it will show you the error on your displacement in time, but also in the frequency domain. So you will show, it will basically do on the fly an FFT of your error, and you can basically then pick up if you have those systematic errors that Salim has talked about. and which we will then basically see by seeing frequency peaks. So here's, I think, the oil column frequency that we're picking up, 25 Hertz, at 148 something else that we're picking up. So you'll see that. Then it will also create basically these subspace plots where you plot command displacement versus measured displacement. Salim showed this. And if this is a perfect tracking, you basically get a line 45 degrees. And it's just a single line. But as soon as you start having errors, there will be some basically ellipse forming here, right? Or if you have overshoot or undershoot, this line will not be on 45 degrees, but going away from 45 degrees. And then finally, if you integrate the area inside that subspace plot and plot that against time, you can come up with this tracking indicator, which was developed by Professor Merkan. And basically, we're creating that on the fly too, so you can immediately see how well you're doing during a test. Okay, now finally, some few slides about the OpenFresco website. OpenFresco website has a lot of resources available, so you can come in here, go on to the users. That's where you can download OpenFresco Express, OpenFresco itself. It has examples. You can give some feedback. There's a developers tab, so if you want to get the source code, you can go and download that through SVN. So that's available. There's a whole bunch of documentation available. There is the command language manual, so you know what the different commands are in OpenFresco. There's a bunch of example manuals. There's some previous from other workshops, some presentation material there. And so you can all download this. Then there's also a forum that we've started. It hasn't been really used yet, but there's a forum for people to discuss things there. That's the idea. And so finally, to give you summary and conclusions, hybrid simulation really requires, as you can see from all this, a real close collaboration amongst all the different experts that are involved in it. So you have people that are really good at finite element analysis. You have people that know very well in the laboratory about control theory and so on. So everybody needs to basically collaborate together to make this work. And so the structural behavior, like I already said, laboratory testing and control. Some people really specialize in computational simulations, how we can make this go faster. People in information technology come in as well. And so you can also look at it really that it fosters the collaboration among all these different communities. So it's a really great opportunity to get involved into this and work with people that have different interests and all collaborate together. OpenFresco itself, this environment-independent software framework, it really provides an excellent platform to do that kind of collaboration, because that's how it's set up. That's the idea behind it, that it's open source, that it's object-oriented, and so people from different fields can come in and really work on this and collaborate together. And through all this, it should really speed up to do a hybrid simulation, all the way from the planning stages to the very end of a test. It provides, as you've seen, already a large library of hybrid simulation integration methods that we have there. It has experimental elements available, a whole library of those, setups, controllers that we can communicate with, data acquisition systems that we can communicate with. We have event-driven control strategies that we can use, and those are also provided together with OpenFresco. So really what we actually need from all of you guys is more feedback. What kind of refinements are necessary? What new features do you guys want to see when you start using this? And eventually, because it is open source and object-oriented, hopefully whatever you guys develop and come up with will eventually come back. And so we can incorporate this and grow the libraries that we have available, so other users can make use of it as well. So collaborate and then also share. So thanks a lot. Only a few minutes over.